Yes, my name is Ulf Wiger. I've kind of an old boy in the Erlang community. I started programming Erlang in 1992. Joined Ericsson in '96, and then for a while I was CTO of Erlang Solutions. Nowadays I'm freelancing in my own company and joined Eternity, was it in May? Something like that. Part of the core team. So I've been asked to talk a little bit about the experience of using Erlang in blockchain technology. And I think we're probably the first project ever to, there have been some minor projects doing, building some blockchain stuff, but not complete blockchains. So there's always a lot of talk about, what is the best language for X? And I think it's kind of a silly question, really. It's kind of like saying, what is the best language for poetry? Obviously, it's Swedish, but essentially, what is poetry? You could say that it's a way of expressing complex ideas. You try to come up with a very elegant design that expresses something beyond just the words. But languages are really shaped by culture and experience. If you wanted to write a poem about quantum physics, you probably wouldn't want to do it in Swahili or something. Not to insult any from that culture, but also your language shapes your thinking, and it's like that with programming languages as well. So once you get into a programming language and you kind of get deep into it, you start understanding how to structure your problem. And as you know, this is a slightly contested theory, but Noam Chomsky decided in 2000 that basically all human languages have a universal grammar, which was a very exciting idea. It may not be entirely correct, but at least it's a hypothesis that's hard to punch a hole in. So what does it look like when you, for example, compare, say you wanted to translate a poem. This is the hello world of Japanese haikus, I think. It's called The Old Pond or something. And there is a website where you can find a bunch of different translations of that poem. And they're probably correct in some sense, but and it's kind of like that with programming languages as well. You pick one and then you kind of dive into it and you let that shape your thinking. Now, I'm a big fan of opinionated programming languages. Erlang is an opinionated programming language. It has a very clear idea of how you're supposed to write programs in it. Now, we can go here from the least opinionated assembly over at the left side. That happens to be some code to detect the Pentium bug. And then on to, for example, the first high-level language, Fortran, which was very math-oriented. You had the everything is an object mindset, exemplified by C++ there. And then Erlang is in the concurrent and functional merger. It's a functional language very geared towards concurrency. It wants you to think about the naturally concurrent patterns in your problem and to model them. And that code, if you want to know, it's really, it just maps a function over a list by spawning a process for each instance and then collecting the results. So anyway, if you look at how languages divide nowadays, I would say that there are a couple of different dividers. One is performance versus productivity, where if you want something to go really fast, and it's a simple enough problem, essentially you would go with C. I mean, there is practically no good alternative. Then you have a bunch of high-level languages. You have Erlang, Python, Haskell, Clojure, for example. There are, I would say that one thing that they have in common is that if you look at, you try to solve a problem, just in looking at lines of code, you usually will have an order of magnitude fewer lines of code in those languages. And that tends to mean fewer bugs, shorter development time. The thinking time is not necessarily shorter, but usually it goes faster to actually implement it. And so I put Java down there. I don't know if I'm insulting any Java programmers, but essentially, if you compare, for example, an Erlang or Python program with Java, usually you would find a order of magnitude difference in code size. So, but on the other hand, you can write some really speedy code in Java. I divided those two in linkable and non-linkable, which makes a difference for us. For example, if we're programming in Erlang and we want to run something really fast, we would like to package it as a dynamic library. And Java is out. You cannot dynamically link a Java library into the Erlang VM. We can do that with C. But other characteristics, you have concurrency. Nowadays, people are really into concurrent code. I mean, writing web server applications back in the 90s, where I was asked by Francesco not to get nostalgic, but back in those days, I guess you would find it in telecoms and a couple of other domains. But with the growth of the web, it really became mainstream. But you will find rather few programming languages that are concurrent by design. And I would say, okay, I'm insulting Java again. I actually put concurrency as an afterthought. With Java, it's a little bit wrong, actually, because it was concurrent from the beginning. It would just, they picked a bad model, and they also didn't nail a couple of things down, which made concurrency in Java really hard. But some of the languages on the top there, Erlang, Clojure actually, Haskell, possibly Rust, have in common that they have a really well thought out concurrency model. And I would say in Haskell, it really is concurrency as an afterthought because they added that a long time afterwards. Now they have Cloud Haskell, which really is an Erlang clone, but in Haskell. But it's well thought through, as everything in Haskell. Another thing is fault tolerance. And again, I would say, well, you have Erlang and you have Akka, which is a Scala-based Erlang clone, essentially. And Cloud Haskell, which is a Haskell-based Erlang clone. Practically no other languages really have fault tolerance by design. Yeah, you can do catch. You can catch exceptions, but that's really poor man's error handling. Normally, if you have a crash in your code, it goes down, and then if it's Python, for example, it gives you it will barf all over you, and at least I really dislike those stack traces by Python, but that's probably because I don't know Python very well. It really scares me. So anyway, if we look at blockchain technology then, at least compared to what I'm used to, there is very little in a blockchain nowadays that's performance critical. I mean, you have the proof of work, which is really performance critical, so much that you may want to push it into hardware. We're using the Cuckoo cycle algorithm, which is RAM restricted. So the idea is that you shouldn't have so much advantage if you can afford to build an ASIC. So if you have, hopefully, it will make for decentralized mining. But anyway, that is performance critical. I would say communication is also performance critical in the sense that you have to be able to handle thousands of connections, partly for the gossiping between nodes and also connected clients. Another thing that's very typical, I would say, about the blockchain space is that it's really a moving target. I mean, the algorithms are evolving. People are trying to figure out how to make this scale. And of course, as an old Erlang guy, Erlang was great great for scalability, but that's not the kind of scalability we were talking about here. It's the scalable consensus algorithms. And that's not, being able to build clusters of 50 nodes doesn't really help you because it's a completely different ballgame. But we need to be able to evolve very quickly and prepare to move to new algorithms and keep extending and rewriting to stay competitive. So things that I think help about Erlang here is Erlang is the heritage from the telecom side was it really was built. What happened? Shouldn't step on the cable. It really was built for evolving systems. Telecom systems basically have like a 10 to 20 year lifetime, and you have to be able to upgrade them in service and evolve them over time, and they're also hugely complex. So Erlang code is essentially designed as many loosely coupled systems that talk to each other via messaging, and that actually helps when you're a team, fairly large team. What are we now, 12? Means we can work in parallel on different components, and we don't step on each other's toes so much. It has also been shown in practice, I think, over the years that in the Erlang community we have a very high degree of reuse. It's very easy to reuse other components. And also this loosely coupled architecture makes it more easy for us to replace different parts. Now, a lot of this is actually down to the concurrency. And I guess you could say that Erlang style concurrency has almost become sort of a mainstay in the, like I said, a bunch of the other teams have tried to copy Erlang style concurrency for actually many years. And you could say that it's a form of lightweight actor style concurrency. But there are a couple of things that are a bit difficult to copy when you haven't sort of built them in from the beginning. And one is that you can isolate, you can encapsulate messaging inside Erlang in kind of a similar way to, if you think about how structured programming and local variables and functions helped you get away from go-to programming. Some of you are old enough to remember GoTo programming, or you read about it in school at least. But actually, in many cases, when you do concurrency programming, you deal with messaging. It's very similar to GoTo programming. You have a main loop, you get a message in, and you call some callback function. Essentially, you jump into some handler that handles that message, and then you return back to the main loop, and hopefully you've updated your state so that you can remember what you were doing and actually be prepared for the next message, which may not have any relation to what you just did. So you keep just hopping all over the place and trying to keep a ledger so that you can stay sane. Erlang concurrency doesn't really work like that. You have threads that actually have their own state, and they can actually block and they can wait and select on incoming messages so that you can handle messages in the order that's comfortable to you. And this really reduces complexity, and it tends to also encapsulate dialogues so that you can introduce new messages, for example, new features, without having them just pepper your entire code with changes. This also makes it easier, helps you to run a distributed team and sort of work on different areas of your code at the same time. So, and I guess, yeah, I mentioned that networking scalability, this is a big problem in the blockchain space, because say you have a node or a system of 10,000 nodes, at least the most straightforward way to make sure that all messages propagate to all nodes is that you actually send it to everyone. So you do broadcast. And so essentially you have to keep track of all 10,000 nodes. I mean, there are ways that you could imagine optimizing this, but it's not easy, because you also have to make sure that all the messages reach all the nodes. But potentially you have to be able to talk to like thousands of nodes at the same time. This is not a big problem if you're using Erlang. I understand that it can be a big problem in other languages, but this is an area where Erlang is extremely strong, so we don't worry about that too much. We don't worry about the VM breaking or not being able to handle. Usually we will run out of file descriptors, and then we have to up the limit for file descriptors, but that's about the extent of the worry. I was going to talk about challenges, so I was kind of racking my brain to find out what we have been suffering from. And I guess one thing is that there are no other blockchain projects except for a few repositories on GitHub that implement some blockchain-related parts. We found a base 58 encoding library, for example. But that limits the amount of components that we can directly reuse in our project. So in a couple of cases, we've had to sit there and look at Go implementations, for example, and then rewrite them in Erlang, which I think in several of the cases was actually a good thing, because finally understanding the code, when you have to rewrite it, you have to really understand the code, and then often you realize that the original code wasn't that good. So then you're happy you didn't reuse it. And also you learn a lot. Now, Erlang does not run on iOS. It doesn't run on Android. It kind of could, but in practice it doesn't. And I don't think personally that that's a big drawback. It's better to focus on the protocols and then write apps the way they should be written, which is the way the platform makers intend them to be written. For example, Apple is very opinionated about how you write. In practice, you end up writing one iOS app and one Android app, and they are not very similar. Your Android app will be Java probably, and your iOS app will be Objective Yes. And no, I mean, security aspects are different. There are so many things that are different. So essentially, you will not run on run the same code on all those platforms anyway. So yeah. Another thing, I mentioned that Erlang is functional. How many of you actually have experience with functional programming? About, well, more than half. How many don't? Okay, a few. So just very briefly, the idea of functional programming is you kind of write many small functions and you don't have global variables, you don't have a bunch of side effects. So each function relies only on its input. And if you know the inputs, you know exactly, it's going to be the same output every time. This actually has repercussions on the code quality and over time, because if you have a function that relies only on its input and you test that exhaustively, after a while you've figured out everything that's wrong about it and then it stays correct. You change something somewhere else, if the code, it's not timing sensitive, it doesn't depend on any other variables, it's going to stay correct. It's not going to break because you do a lot of stuff around it. And this has been an experience too with Erlang code that, you know, it's fairly easy to reach fairly good quality, but then quality tends to just get better and better, and it tends to get rock solid. You know, when you don't change code, it doesn't break, and eventually it can become almost error-free. And this, of course, is an amazing advantage. Another thing that functional programming tends to be very good at is that it has very powerful set operations. If you have lists of objects, you can do a lot of, you do a tremendous amount of list processing or set processing in functional programming, and it's very good at that. And that's actually something you do a lot when you maintain the state on the blockchain. So I think it's a very nice language for writing the actual core blockchain code. It makes it, I think we have some pretty powerful blockchain state logic now that feels well prepared for whatever consensus algorithms that are gonna emerge and that we may move into. And then another thing about Erlang is that it really it was designed in the telecom industry. It has been used in high availability products for 20, 30 years now. It is really rock solid. And they maintain backward compatibility religiously. You don't really have to worry about if a new version comes out, your old code is going to work. It's even going to work even if you don't recompile it. And it is just extremely stable. And this also gives you a lot of peace of mind because you don't really have to worry about that. It also really minimizes the dependency hell of having third-party libraries that depend on different versions of some other. We don't really have much of that. And I think it's part of the mentality of the community. And then the networking support. One of the things about having a virtual machine that has dynamic memory management and all the data is dynamically tagged, many of the typical attack vectors on network sockets simply don't work in Erlang. So if you look at Erlang-based web servers, for example, there are very few security advisories on them. It is pretty hard to attack a well-designed Erlang system. So I put these last because this is just basically for the Erlang programmers what we are actually using. The OTP components we use, the Mnesia database, and then some of the web stuff, SSL, and inets, also runtime tools for tracing, and then we have the core apps that we are building, and then we have some external components that this is a C++ code, the Cuckoo cycle proof of work that we have built our own wrapper for. We use RocksDB as actually a custom backend for the Mnesia database, which is Erlang based. We use Exameter for metrics, Cowboy for the web server, JSX is a JSON parser, YAML, base58 message pack encoding, JSON schema validation. IDNA is DNS naming for applications. Salt, SHA-3, these are also C libraries with Erlang wrappers as NIFs, sort of dynamically linked in functions. And then some of the basics, poolboy, gproc, stuff that most Erlang projects use. And then for build and test, we use Rebar 3 for build. Could be better, but it does the job mostly. eUnit and common test, pretty powerful, I think. I especially like common test. We use Dialyzer, we wrestle with it, but it's really helpful. And then having the Cubic team on board and using quick check models is extremely helpful. You're going to hear more about that later. And then we actually use Python for the acceptance test. We feel that it's actually good to sort of step out of the environment and have a completely separate environment for that test suite. So, do you have any questions?
I just wondered why you chose Cowboy out of all the other possible websites.
Actually, it was partly a side effect of using Swagger, which I wouldn't recommend. I think we are, I didn't mention Swagger. I try not to mention Swagger. The JSON schema part is nice. The generated code for Swagger is just awful. You don't want to use that. We're working on actually restructuring that so that you can use Swagger's schemas with this is basically using JSON schema for the client-side protocol or API, and then generate validation code. And then, for example, you can use Cowboy for your server, inets, for example, for the client, and then we can call the validation code on both sides, so we get the schema validation, because you don't really need help with the other stuff. It's easy enough to write a web server callback module with Cowboy, or whichever web server. We happen to end up with Cowboy, but so Swagger doesn't give you any additional help. You have to write the same callback module as you would have if you used Cowboy directly. Swagger just trips you up in 1,000 different ways. So,
if you had something against, say, yours.
No, I've been using yours before. I don't really think that's. I think it's pretty much a matter of taste which one you pick. I mean, they have their quirks, and their strengths, but they're pretty good, all of them, I would say. At least I don't have a particular preference. Yes?
What problems did you have with Rebar?
Problems with Rebar. We have found that, for example, that usually after you've done some merging, you need to just pretty much scratch the whole build directory and start from scratch, which it's frustrating if you don't, because it doesn't really tend to clean that well between builds, and so you can get some really weird errors if you don't do that. But then, of course, you have to go through, all the dependencies and recompiling everything, and RocksDB takes forever to compile. But that's not Erlang, that's C++.
Did you use? I think I'm okay with that.
Yes.
Did you use the Cuckoo? You implemented a wrapper around that. You call that from Erlang, I guess.
The Cuckoo wrapper, yes, and
So next to that.
it used to be a NIF. Then we got tired of seg faults and stuff like that, so we actually rewrote it so that we're spawning using Erlang sec actually, and creating separate processes for it. Now the overhead of creating the separate processes is nothing compared to the cost of actually doing the proof of work. So we don't really gain much by having it as a NIF. It just complicates things. I mean, one thing about having a NIF, if you get a crash, you get the core dump from hell, because it's the entire VM and then some dynamically linked C library. So usually it's almost impossible to debug. It's hard enough to debug a normal core dump, but a core dump of code linked into a virtual machine is no fun at all.
So I was just going to ask why C++?
Why C++ for the Cuckoo cycle? You'd have to ask John Trump. Does anybody know why he picked C++? He really shouldn't have to have done that, I guess. Maybe he just used it as a better C, which is why a lot of people use C++. Yes?
No mention of Go on any of the slides.
No mention of Go. Yeah, that was accidental, perhaps. I'm still trying to kind of place Go in the... it actually has some nice concurrency support. What I personally lack or miss in Go is the fault tolerance. And also I'm kind of waiting. It's the same thing with Rust. I put that in parentheses. I think they still have to prove themselves a little bit in terms of, at least in terms of sort of real robustness in the concurrency and complex concurrent applications. But I've noted that quite a few of the, I mean, Go is actually a language that is used in the blockchain space. So for example, the Merkle tree implementations, we looked at the Golang implementation and decided it wasn't that good. So I think ours is better now. Yes?
Just one note here, side note. C# is also not here. But C# has lightweight threads like the Erlang process. And also with Service Fabric, it's completely fault tolerant, the same as microservice architecture with like actors. So just a side note that C# is actually covering most of the criteria.
Yeah, that's true. C# is, and it's interesting with the .NET ecosystem, and I did talk to Eric Meyer some years ago about the evolution of, he's kind of trying to implement Haskell in .NET, and they are adding a bunch of stuff. So essentially, I I did a presentation some years ago, I don't even dare to think how many, about how to do structured network programming. And you can do it even in plain C if you think about it. And one of the things you really have to think about is proper scoping of messages, essentially what I was talking about. And you can do that. They also have channels, essentially. So you have there were a bunch of languages I didn't mention, F# too. And basically, I mean, the part of my point was, yeah, you can do this in a lot of different languages. It works well to do it in Erlang. I wouldn't say that Erlang is uniquely suited to the blockchain space, but it works really well. And in some areas, I think it works extremely well. In other areas, possibly roughly as well as some of the other languages do. And I can't really think of an area where it's exceptionally weak, where we feel that we really suffer from using it.
So,
Yes?
Ken Thompson role when he asserts how good Go is.
Well, I don't want to knock Go. I know that some of my Erlang friends are quite pleased with Go and actually prefer it over Erlang in some, at least in some spaces. So I don't know. It seems like it's doing quite well. I think Erlang and Go have slightly different focus areas, kind of like Erlang and Clojure. Clojure also is a very interesting language, has a very interesting concurrency model, but it attacks a slightly different problem space than Erlang does. So again, you have to sort of get deep into the mentality of a certain language and then build from there, and build on its strengths and then try to figure out how to compensate for its weaknesses. And that's what you always have to do. Yes? Okay, so I guess we're still ahead of schedule, so. And no more questions? Thank you.